Hey guys, how's it going? Hope you are having a good day. I am excited to chat about local outlier factor. Before we get into it, I want to remind everybody we are growing our Discord rapidly, completely focused on data science. We're helping people build stuff, people are asking questions, people are helping each other. So I highly recommend joining it if you are working in the space or you're in school for it or anything like that. Always want to help people build stuff and do things like that. So I highly recommend you check out our Discord. All the code for this video and the other ones is put there as well. So if you want to try any of the stuff that we build, you can find the information there. So local outlier factor. This is another anomaly or outlier detection algorithm. We'll also see in the next video a look at it used as novelty detection. That's a slightly different approach than the anomalies and the outliers, but today we're just going to focus on using LOF. You'll hear me call it LOF for these anomalies and outliers. This is an unsupervised algorithm. If you're not familiar with what that means, it means you can identify these data points, these anomalies, without prior labeling, having a labeled data set, or anything like that. You can just give it a set of data points and it will calculate and sort of work through to figure out what the anomalies are. To kind of dive into a little bit of how this is different from some of the other algorithms, the way it really works is it considers the outliers of the samples that have substantially lower density than their neighbors. We'll do a walkthrough and kind of see what that looks like, but very focused on looking at a data point and understanding based on how close its neighbors are, if that means it's an anomaly or not. And we'll talk about like defining a radius and things like that, but that's going to be the general premise there. So kind of a high level of how it works. The algorithm produces an anomaly score for each data point by measuring the local density deviation of a given data point with respect to the data points near it. Just like I mentioned, we have a data point, we have data points around it, we have some sort of distance between those, and we can use that to calculate which ones in the data set are anomalies and which ones aren't based on those neighbors. Local density is determined by estimating the distance between data points and their neighbors, like I just said. By comparing these scores, we can understand which data points have similar densities and which ones have lesser density when compared to the neighbors. That allows us to create these K distances. You'll see me reference that a little bit here and there. That's the distance between points that are calculated for each point. So here we go. Let's take a look. Let's say our point is here. We have all these other data points here. The K distance is going to be the distance around those points. It's just a calculated distance, based on what the values are there. We can see the K distance of these various neighbors to a single point. So the K distance is used to calculate the maximum of the distance between 2 points and that K distance of that point. From there we can sort of see with the radius and the calculated distance, start to sort of gather what's the density of the points around this one point that we have. Now we can take all of the K nearest neighbors and calculate the local reachability distance. So we have all of our neighbors around this specific point. We understand the distance between them. Now we can create this new score, which is really a measure of the density of the K nearest points around a point, which is calculated by taking the inverse of the sum of all the reachability distances of all the K nearest neighboring points. The closer the points are, the distance is lesser, the density is more, hence the inverse is taken in the equation. Very long way to say that, of course, if we have more points and they're closer together to this single point, our distance, our K nearest distance, is going to be smaller. And we, of course, have more neighbors from that point as well. There's a longer form equation to do that. I didn't really want to focus on that as this is much more use case specific, but you can see kind of how we're getting here to create this. You'll sometimes see this called LRD and stuff like that. You might see that mentioned if you read like the paper and things like that, but really trying to understand the density of the points, and then the distance as well with that density. So if the density of the neighbors and the point are almost equal, we can say that they are quite similar. And if the density of the neighbors is lesser than the density of the point, we can say that the point is an inlier. So now we're starting to be able to form, based on these neighbors and based on how many there are and how close they are relative to the rest of the points in the data set, we can kind of start to say which ones are an inlier or an outlier, which ones make sense, which ones have a cluster. We can start to, when we understand for one point what this sort of radius looks like around it, look at all the points in our data set and their radius and start to figure out which ones are outliers and which ones aren't. So this is a look at what we have. This is a nice graph example. I've seen this a lot used for LOF. It's one of the better ways to be able to view what we're talking about. Here we have a bunch of data points, and then we have an outlier score calculated for each of those based on, like we said, how many neighbors are around it and how far are they. You can see that as points sort of move closer to clusters, and you now have more neighbors, you can see that the circles get smaller. The larger the circle, the more an outlier it is. So that is kind of an interesting way that you can see the way that the neighbors aspect of it works. A good example is this point right here. You probably think that's got to be an outlier. Like there's really nothing around it, especially when you compare to these two and these two, which have larger outlier scores. They're more of an outlier at this point where you're like, how can that be? Like these two are really close and these two are really close. But this point is much closer to this massive cluster of points we have here. So when we calculate distance scores of the nearest neighbors we have for this point, it's these, it's probably this, and then it's this huge massive blob. So that score is just so, it gravitates so closely to these points that are incredibly dense. We have all these neighbors with all these very similar distance scores, whereas these two, although the score between these two is very small, they're very close, you don't have these other massive clusters as close. These aren't as close. This isn't close. You just have, when you look at the number of neighbors that you have and how far away they are, you just don't have as many. One thing to keep in mind, we'll see it in the code, is that when you calculate local outlier factor score, you decide how many neighbors to use. So you decide, do I use 5 neighbors? Do I use 20? Do I use 30? You decide what that number is. That's not something that's dynamic. That's not something that changes. So for this point, if let's say we're using 10, closest neighbors, all these are the 10 right here. Like they're all 10, maybe you have maybe this one's close enough that it's used, but all of these are used and they're all incredibly dense. They have a very tight outlier score and they're all relatively close to this. So you have this is less of an outlier. When you go to these two, you say, well, what are the 10? It's this, it's this, maybe probably not one of these. You do probably still have some of these, but they are further away. They're further away. So although they are very dense and some of those will count, not as many as this point would have because, this point has this one, it has this one, but they are further away. So it's not taken into account as much. So that is something that is very interesting to see, the sort of way that clusters of points really affect the points around it as well. When you look at sort of this local score, right? Local to each point, and that number of neighbors to use, you're going to see is taken into account very heavily. And we'll talk about how to choose that number and things like that. But this is one of my favorite graphics of LOF because I think it does a great job of showing how clusters work and then how, as points move away from clusters, the circles either get really small or really large. This is a graphic you've seen before if you watched my isolation forest video. This is one of the more popular graphics when comparing anomaly and outlier algorithms. It has a couple different data sets. It has 5 different data sets, and it shows how different models work on this. Let me move this over here so that LOF is over here. Has 5 different ones there, and it shows how the different algorithms do. Couple things to note with LOF specifically. You can see how it works here compared to some of the other ones. It does a really good job on pretty much, sorry, I'm looking for my cursor. It does a really good job on pretty much all of the data sets. One of the most interesting ideas with LOF compared to some of the other ones is the very high focus on clusters. That's not something you see as much with some of the other algorithms, where they have much more of a bound around that decides it. Essentially, they build a bound around what are clusters and what aren't. LOF doesn't do that. It does it point by point. So you can get things like this one here that, you have sort of these very interesting waves here that we have. Isolation forest probably does the best outside of LOF. That's just because it's really good. I said that in my last video. Some of these other ones that assume the data is Gaussian and things like that, they don't do as well. Isolation forest does not, so it does much better. But LOF, being that it is localized to each data point in deciding if it's an outlier or not, does really well. I mean, these are essentially perfect understandings of what the outliers look like, especially compared to things like that. That one's it's pretty good. I don't love some of the bounds there on the ends, but it's not awful. But just a really great split there that we can see. You can see it does very well in some of these data sets as well. Really understands this density cluster. Understands that this one here is a pretty good cluster as well. So it does allow us with that localized understanding to do really well on some of these more unique data spaces compared to some of the other ones that either assume data is Gaussian or require a lot of fitting and things like that. The localized nature does not require that, which is very nice. So let's take a look at some code. If you watched the isolation forest video, you have seen this data set before. This is the same data set we used with the queries and the query length. Let me load this up. We can take a look at what that looks like. I need to rename this for my code. So let's load it into a data frame. You can see, so the first column is going to be queries. These are like chatbot queries and Google search queries and things like that. This is a real world use case data set for us. We build a lot of metrics around search systems and the chatbots that we build and things like that. We want to build metrics to track the ability and everything like that. And so we build models like this to recognize when a user is using too many queries or queries are too long, or they talk about specific topics and things like that. All of that data is tracked and analyzed, and models like this help us do that. This is a little bit more of a simple use case, but this is one that we use as sort of a foundation of a lot of these sort of metric and evaluation tracking tools. So we loaded it up. I am going to load this up as well because I do like to do 2 different fields instead of just one. I don't really think it's relevant to show you guys just a single column and show you anomalies based on one. That's a really simple use case. There's not a ton of those in production that actually exist. So I built this little code script to use the Spacy noun recognition model, the NER model. So it recognizes what, nouns and proper nouns in the queries, and then it does a count for each of them. So we can see here, we have our original query, we have our query length in characters, and we have our noun count. And what we're going to do is we're going to generate the anomalies, we're going to figure out which data points are anomalies based on 2 fields, not just 1. So that does mean our graph at the end will look a little weird because we're going to be looking at a 2D graph. But it's a little bit more relevant that you're going to be using more than just 1 column when you do these type of use cases, especially if you're generating a lot of metrics. We're using 1,000 rows, 1,000 queries. We see we have our 3 columns. So pretty simple code here where we load up the model. We have a function that just runs the Spacy model on it, counts the tags that contain. So what Spacy does is it'll go through each word and it'll figure out, is it a named entity or not? And then it tags them. So it tags them like noun, proper noun, different stuff like that. And we just look for how many of them have noun or proper noun, and then we count it up. We just take the sum, as you can see, and we return it. It's simple function. We just run an apply on it on a pandas data frame. We run the apply to a new column called noun count. Pretty simple. So let's load up our model. We are using the Scikit-Learn LOF model as well as the train test split. So we convert this to a single field. I believe that converts it to a NumPy. I can't remember off the top of my head. I believe that's a NumPy array. But we have split it now into the X train and X test datasets. Now, we are going to load up an LOF object. We do get to pick now the number of neighbors that are evaluated. This is probably one of the more frequently asked questions I get, which is how many neighbors to choose. 20 is the default number written in the paper. Most people go with 20. I guess unless your data set was tiny, then I guess you should probably sample up and down based on that. Most people don't go outside 20, even with much larger data sets than what I have here. That's the one talks about in the paper. The paper does talk about the sampling up and down based on it, but you do get to pick this number. One of the ones that I always mention is that there's nothing wrong with picking a larger number. That this is just how many neighbors are evaluated. It doesn't really, it doesn't negatively or positively affect your data set results. It just is the number that are evaluated. I will say that through experience, the larger the number, generally the more accurate the results. And that's a pretty easy concept to understand. I am increasing the number of data points to evaluate. I'm increasing the scope of what I'm allowed to use. It just kind of makes sense that you're going to be more accurate. It's like if you built a classification, text classification model, and you used 20 data points, versus 100, and then you ran real data points on it, it's seen more data. And so it's generally going to be more accurate. That's kind of a weird analogy. But you can kind of see as you use more data points, more neighbors are evaluated, then for that single data point, you have a better understanding of what is an anomaly around you when looking at all the data points and all of their neighbors. So I'm going to stick with 20 for this, but there's really nothing wrong with choosing a higher number. It does increase algorithm complexity, so your algorithm will be slower. You just have to do more k-distance generations, and things like that. You have to do more of that evaluation. But it is probably going to improve your accuracy. So kind of up to you. I'm going to use 20. Contamination, that's another one I get asked about quite a bit. Contamination, it's kind of a weird one. It's the percentage of your data set that probably is an anomaly. That's probably the best way I could say that. And then people when I say that, people go, well, how do you know what the how I'm running this to see what my anomalies are? How am I supposed to know? It's just a general guess or estimate. The paper uses 0.1 as the default value, so most people use 0.1. There isn't a ton of harm going up and down. Your error rate is probably going to change slightly based on going up and down, maybe some more false positives and false negatives. But I would just stick with the default. This is not a number that for most use cases you're going to want to be playing around with a ton. And quite honestly, isn't probably going to change life for you in most use cases that are on the simpler side. Maybe you start getting into some use cases that have a lot of dimensions in your data space. Your contamination probably matters a bit more, but I would stick to 10% here. That's the default one. Sometimes you'll see 5% used. It's fine as well. Something to play around with. So we create the object, and then we do a fit predict. We fit the data, and then we run our predictions of what our anomalies are. So fit is running the algorithm. Predict is going to say which ones are what. And now we can go from there. So when we look at the results array, we can see for our data set which ones are anomalies and which ones aren't. Ones are inliers, negative ones are outliers. So you can see for each data point we had each of those rows, 1, 2, 3, 4, blah, 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 and go on from there. I'm just viewing the output results. That's why you don't see column, 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 anomaly. I'm just looking at the output array that is being fitted. But you can see here we have our values. The algorithm went through, said these are inliers or outliers. And it's very clean. It's very easy to look at. There's no like thresholding and things like that. It's just, is it this or is it that? Which is nice. So now we are going to, maybe I should have done this step above, but I'm just attaching this array to a data frame column anomaly. So now this is all one data frame. That's everything. Maybe I could have done that above, but I wanted to sort of show what this array looks like on its own. So you can kind of get the feel for what that is there. So let's plot this. Let's take a look at our data. As I mentioned before, this is a little bit of a weird data set to view because I'm trying to figure out what's the best way to do it or to say this. It's a little bit odd because we are using two values. So that does make things a bit different. You can see here red is anomaly and blue is not. Pretty interesting results as we can see here. You do see a little bit of clustering going on here. You see a little bit of clustering going on here. Although this one did come out as an outlier, which is kind of interesting. I am pretty surprised that these came out as outliers as well. Or sorry, not outliers. I'm surprised they came out as inliers, considering kind of their relevancy to the rest of the data set. Stuff like this, very unsurprising. You just look at the neighbors around them and you just don't, these neighbors around are outliers as well, much further away. Not super surprised. This one, same idea, very far away from everything. A little bit surprising there. I am curious to see how adjusting some of these values changes the results. Because you won't know, I look at this and you might go like, how do I know if this is correct? And just based on this, you really don't. I mean, if you don't know your data set and know which ones are the outliers, in sort of a test environment, it's a little bit harder to sort of quantify what that is. Visualization and things like that helps. But it is something that in a real production use case, you should be testing on a small size with a, sort of actually labeled data set. So you can get a feel for what your error rate is, your false positives, your false negatives, everything like that. But, when you don't have that, you really are just relying on the unsupervised nature of the algorithm to, show us what we have here. So that is LOF. I hope you guys enjoyed. Feel free to leave any questions or comments down below. I hope you can implement this and play around with it. It is one of my favorite ones to use. I love the unsupervised nature. I love the localization factor with a lot of those data sets like we saw that have very high cluster rates and things like that. I think it works incredibly well. It definitely outperforms some of these support vector machine style approaches in those regards. But hope you guys like it. Feel free to ask any questions, and I'll see you guys next time.